when I was talking about the Sharky Devil point, I was trolling. That's not a viable thing, and I think it's way too obscure. So I'm not gonna waste your time on users configurations, I guess. So instead, I guess I'll discuss the configuration I think is more useful. And I was motivated to talk about it because of recent problems. Ahem ahem. I posted the handout in the classroom. You can read it. Hopefully you are wowed by my problem set. Okay, let's start another damn whiteboard. Okay, screw this. So, the configuration, as you might see in the handout, is we start with a triangle, I believe. Yeah. Okay. Yeah. Okay. Let's start with let's start with any old triangle. Where's move? Okay, let's move. So we start with an arbitrary triangle here. Oh my god, what the hell is this? So yeah, triangle drawn. We draw 3 circles. Like they're basically the circumcircles of triangles erected on the sides. Okay, let's draw those. Okay, beautiful circle. Indeed. Okay, second attempt. This is epic. Okay. So once we get that circle, then so yeah, we have to draw like 3 of these. Ew. Please don't bother with the excellent quality of these circles. Okay, draw. I've never used this damn Zoom whiteboard before. Okay. So once we okay, that is disastrous. Who cares about this end of the circle anyway? Once we get to that, so the theorem is that if we like look at the 3 angles I'm drawing right now, so if these 3 angles add up to 180 degrees, then the circles are concurrent by angle chasing. I think that's a pretty straightforward proof, but I don't know if I should go through the details or not. It's not the Michael point. Michael point is a special case of this. So well, I guess I'll start with the motivating example. I think many of you will recognize it because I wouldn't dare to say most. Okay, so this is this year's USIMO number 1. That's what inspired me to use this topic. Okay. So once we draw the triangle, then we have to draw rectangles on all the sides. Okay, why won't the damn thing rotate? Okay, screw this. Okay, whatever, just draw the rectangles. So we erect rectangles externally, like so. Oh my god, what is this? What is it? So we draw stuff like this. The rectangles are drawn externally on the 4 side. No, not 4, 3. Oh, I'm so sorry. So the 4 sides, and then we're given that like this angle. Okay, let's draw it. So this angle over here plus cyclic variance is equal to pi. So once we do it, the first thing I did when I saw the angle condition was to draw the circumcircles, probably because I've seen it before, but I don't know how you think to do that if you didn't see the configuration. So yeah, okay, let's draw the cyclic variance. they're supposed to sum to 180, but who cares? So yeah, once we do that, so once the circles are drawn, the problem is pretty tractable, I would say. So once we observe that the circumcircles of the rectangles are concurrent, then let's assume they concur at a point P, say. Okay. This is laziness. So that circle, another circle. Drawing them manually was this. So this circle and a third one. And changing colors takes too long. Whatever. So yeah, these three circles we'll assume they concur at a point. So like the concurrency point is P. Let's just call it P for now. So once we do that, the claim is that like I was drawing the three lines we were asked to prove are concurrent, which is this. How do I change the color? So we're asked to prove that this line, okay, that's a terrible diagram. This line, cyclic variants include, which line was it? This, yeah, I think so. This one, that one, what's the third cyclic variant? Okay, there. The diagram is bad, but the three blue lines are supposed to concur at the point P, which is like here. Okay, what an embarrassment. Now let's adjust the diagram to make it look like that. I guess this is the importance of drawing large-scale diagrams. But like, yeah. So the claim is that the P is the concurrency point of all three lines, and W log we only need to prove it for one of the lines that it passes through P. So we draw this line, and this angle is. Wait, can you see my mouse cursor? Just asking. Oh no. Okay. So this angle is equal to this angle. Okay, let's just mark it. So we start with this angle, which is right because it's equal to this angle, which is right. So yeah, this is a 90-degree angle. And then on the other side, we also have a 90-degree angle. So this line passes through P. And then similarly, all the other lines pass through it. So we're done. Bruh. Motivating example, unmotivating explanation. Okay, so that is how I was inspired to do this configuration. There's another one that I'd like. There's a classic example I'll show. It's the Outer Napoleon triangle thing, but I guess this configuration offers an angle chasing proof of that. Angle chasing isn't fun, but I guess you have to do it anyway. So everyone, I think people in this should know what Napoleon's theorem is. And for those who don't, I'll draw the diagram. So in any triangle ABC, we draw equilateral triangles on each of the three sides. And then the centers of the three equilateral triangles form an equilateral triangle themselves. I guess I'll actually do some labeling this time. Okay, second triangle. Third triangle. Libra. Asymptote would have been so much faster. Don't bother with that. So once we do that, let the centers of the circles. To answer the question, Napoleon is a special case of the configuration. Well, it's not. Well, actually, no. Never mind. So it's like we use the configuration to like show the thing. Okay, so let me draw in the centers already. Beautiful centers here and here and here. So the angle chasing proof of Napoleon's theorem is, first we draw the circumcircles of these three triangles, and they're concurrent at the Fermat point. That's the only point that satisfies like AFP equals BFC equals CFA equal to. Okay, why haven't I labeled the vertices? What am I doing? A, B, C, D, E. It might be labeled differently on the handout, but who cares? I'll just call this P, Q, and R. Okay, so when we get to that, we're gonna draw the circles of that pass through ABF, ACE, and BCD. Okay, draw a circle. Whoa. What a circle. What a circle. Okay, I'll just call that a day. Okay, who needs perfection anyway? The three circles, so okay, finish drawing them, I guess. So yeah, this point is the Fermat point, and then like, so obviously the most straightforward way from here is just to prove that one of the angles are 60 degrees, because then the other ones follow by symmetry. So then I don't know if anyone actually read my handout, but like, once we draw this line, when we're trying to prove this is 60 degrees, we're gonna need a lemma. So okay, draw last circle. What is this? Okay. From here, this point, let me label it F. It's the Fermat point, as mentioned earlier. Okay, why am I drawing this? So yeah, this point F. So we split the angle RPQ into two angles, RPF and FPQ. And then by symmetry, FPQ is half of angle FPC. And similarly, RPF is half of angle BQF. So the whole angle RPQ is half of the angle BPC, which we know to be 120 degrees. And because RPQ is 60 degrees, then the other angles are also 60 degrees by symmetry, and we're done. I don't know about the length chasing proof of this, but yeah, I guess this is the nicest proof I thought of. And the rest of the handout, I put a lot of problems. Maybe you should try to do them, and then we'll reconvene in a short while, I guess. Okay, I'll construct the diagram first. Question, is my hand having a spasm? No, I'm just trying to click erase because I don't know why I'm not smart enough to hold the mouse down. Okay, start with the diagram again. It's another triangle, nothing novel here. Okay, let's start with the less than novel triangle. Equilateral triangle here. Perhaps I shouldn't propose problems when my brain is not functioning. Equilateral triangle here. Hexagon, who cares about the distant points anyway? Okay, hexagon here. Beautiful hexagon. And that thing goes off the charts, but who cares? Okay, now we draw the circle. Now we draw the circumcircle of this. Okay, circle. Okay, circle, that's an ellipse, but who cares? Again, so I'm gonna assume this point is like down here. Most of this hexagon doesn't matter in any case. Okay, I'll just eyeball and say it's over there. And this point we label, okay, label the vertices now. A, B, C. I think we're probably gonna have to extend that. So then we draw this point intersecting that thing somewhere over there, somewhere over the rainbow. Okay, I'll just eyeball it and say something. Don't bother with the straight line, basically. Or maybe I will bother with it. Okay. Underwhelming people since 2018. And the passing through this vertex of the hexagon is just a coincidence, by the way. Okay, it intersects somewhere down there. Wait, why am I revealing the solution to the problem? So in any case, we're supposed to prove that these three lines concur. Yeah. Oh wait, am I trolling? Okay, that's a bad diagram because I cannot draw lines to points correctly. Somewhere. Yeah, something like that. They're supposed to be concurrent. So yeah. So the proof of this goes like we noticed that for these three lines to be concurrent, if we extend this to an intersect somewhere down there, then it's equivalent to showing that AC and this point and that point, like they form a harmonic bundle. So then we can so then if we look at the thing from the perspective of K, that's just an angle chase, and we can just use an angular property of harmonic bundles. So what we end up with is that this angle is supposed to be 150 degrees. Okay, let's label it 5 over 6. Yeah. So yeah, that thing's supposed to be 5 pi over 6. Because like when we intersected this line with this circle, this angle was 120 degrees. So this angle is 60 degrees, and because the arc on the hexagon circumcircle is 120 degrees, it follows that the point K is also on the circumcircle of the hexagon. So then we look at then we have this angle is 60 degrees, I believe, because pi minus 120 degrees, very inconsistent. This angle is also 60 degrees because like here, this is 60 degrees from a 120 degree arc also. And finally, there is a 90 degree angle. Where the heck is it? What? Where the heck is this? Am I trolling? Wait, what? Yeah, so there's like something is 60 degrees here. 60, and there should be a 90 somewhere, but yeah. Yeah, oh yeah, the 90 degree is this angle. This angle here is 90 degrees because this is 150 and this is 120, so this angle must be 90 degrees. Once we obtain that, then we can just use a well-known theorem, and it follows that AC, this point, and that point, which are unnamed, are a form of harmonic bundle. And then it's just Menelaus theorem and Menelaus plus C1 or done. Cancerous proposal. In any case, I wrote the problem set off the top of my head. I guess I'll go through the first problem. So I think it's pretty obvious at how to start the problem. Where is that? Okay, let's use a whiteboard. Okay, that was a terrible proposal. Let's not propose problems in the middle of the night. There. Again we have a triangle. Like I guess like 60% of geometry problems involve the word triangle. Okay, I guess that's one of the monotony. That's a bit of the monotony of geometry. Given that, so we're given two triangles. Let's just put one here for template purposes. So yeah, a template triangle like this, and we are asked to like, I don't know what this is called, but we're like, this triangle is supposed to be inscribed in a triangle similar to this one, and we're supposed to construct that like the opposite of inscribed triangle. It's, I don't think circumscribed makes sense, so I'm not using that word. So yeah, we're supposed to construct some triangle that looks like this and is similar to another given triangle. So obviously we note that these angles are all fixed. So they lie on three fixed circles, which are concurrent because the angles of a triangle sum to 180. Next. What a piece of artwork, to be honest. Okay. So these circles are fixed. Okay, let's draw. So yeah, these circles are fixed and concur at a fixed point, therefore. Then we're looking at like the length of this. Then we're looking at like the side length of one of these, since all such triangles are similar. So let's say we're looking at like this length. So it reaches it, and it always has to pass through this point. So yeah. Then how we could look at the longest such segment is because like by spiral similarity, this all triangles of this form, like this triangle, they're all similar. So we can just compare a corresponding quantity. Put like a triple Venn diagram, indeed. So yeah, when we're comparing distances, the distance, because it always passes through this fixed point, the distance is maximized when this line is perpendicular to it, where this point is fixed and so is this. So we have a right angle here when it's maximal. No, what is this? Yeah, right angle here. So right angle here is the construction. So in practical case, we would construct the circles, then draw the lines through that concurrency point to the vertices. Then we would construct perpendicular lines at the vertices through the three drawn segments. And then those three lines would form the desired triangle. So yeah. What a clear explanation. And I didn't prepare any other problems because I literally wrote this part off the top of my head. Oh yeah, this is some boomer age IMO problem. I was grinding IMO, so I saw it and put it in because off the top of my head. How do you, interesting question. How do you grind IMO? Well, you just go through old problems, I guess. And that includes ISL. Well, it's in general, it's ISL grind, but like, yeah. ISL grind is not cheating. What do you mean? What are you talking about? It's perfectly fine to grind ISL. I would say that I only just got started. Okay, that's not relevant in any case. 。  . 。  . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 .
。
Okay, let me try to think of another example because I'm so original. The angle is right. So like when we're trying to maximize so this line passes through a fixed point. Then we're trying to maximize the distance from this point to this line. And because this line is fixed, the foot of the altitude from this point to this line lies on a semicircle with this diameter. I'll explain it in detail now. So on this semicircle, the point farthest from this point is clearly the antipode, which is this point. So yeah. I think that the original problem was worded even like worse than my wording on the handout, but like, yeah. Overall, old problems, old IMO geometry problems involve a lot of loci. Instead of like triangle ABC, blah blah blah, some BS. So yeah, hopefully I did not waste too much of your time on the not the Sharky Devil point, but like yeah, ha ha ha. It would have been so much less hassle to use asymptote.
All right, so thank you for coming. And so a video of this will be uploaded later. And so on next Monday, there will be another 4 questions released. And next Friday, we'll have another guest lecture. And this time it will
be reconvening?
Yeah, next Friday.
Wait,
and next Friday's guest lecture will be by Alex Chen.
What will he be talking about? Oh yeah, Aaron, do you know what he will be?
Yet, but it's probably some algebra problems, I think.
Okay.